Hello. So we're going to look at graphs from the perspective of the McAllister slides. These slides, there will be some repetition from the previous video in terms of definitions. We will look at most of these chapters, but not all of them this time, and then we'll pick it up with shortest path algorithms and topological sort. So, as I mentioned in the previous video, graphs are a superset of trees and linked lists. You've already dealt with trees and linked lists, and you've drawn trees as circles with integers or letters in them. The graphs are very similar. The additional part is that there are no cycles in trees or linked lists, of course, and graphs remove that that constraint. So they're represented in several ways that we'll get to. They're accessible in key field mode, in other words, by listing what the key is, or in node number mode. They have the four basic operations like insert, fetch, delete, and update, and usually a traversal. In our case, in this case, for graphs, usually a breadth first or a depth first traversal. There are all sorts of algorithms, Warshalls, Prims, Dijkstra's, and we will look in detail at some of these and not so much in some others. Now, graph has a distinctive terminology. It was developed differently from trees, although they share some features, but that it has distinct terminology. So we'll talk through that. Some of it you've already understood from and studied from the previous slides. Nodes in a graph are referred to as vertices. They're as with trees, they are drawn as circles with integers or letters, usually capital letters, or perhaps with a graph, there's more information in the node, in the vertex, maybe a city name or something like that. They're connected with lines or arrows. So just like a tree has implicit arrowheads from top to bottom, that the only direction that theoretically you can travel is from top to bottom in a tree. And a graph has a similar situation, but it also may have an undirected graph, may have an undirected edge, which is arrows, represents arrowheads in both directions. So that's unique, things that are unique to trees with graphs. There are also a few features of graphs that are unlike a tree. Edges can connect any two nodes in a graph, like the one at the top right. Let's look at the one at the top right up here. Any two nodes can be connected. Now, an interesting thing that the slides don't say, but when you go to delete an edge, when you go to delete a node or a vertex, an edge doesn't exist without two endpoints. So if you were to delete vertex A, you would end up also having to delete these two edges. Edges can be bidirectional, or if not, if they're and normally when edges are bidirectional, all the edges are bidirectional. It's called a bigraph, a digraph, directed graph, and you don't put the arrowheads in. So also you can store weight information. In the previous set of slides, they were mileages. They could be mileage. They could be amount of effort, any kind of weighting. And they don't need to be adjacent. So here's node B is disjoint from the rest of the graph. So where did graph theory come from? Well, there was a guy, Leonhard Euler, a mathematician, who apparently had nothing better to do, so he posed the following problem. He lived in Königsberg, with the umlaut over the O, which is in northern Germany, perhaps Poland, I'm not sure exactly where. And the river flows around an island called Niepow. And like the diagram below, there are 7 bridges and 4 land areas labeled A, B, C, and D. A, B, C, and D. And so, and the bridges are labeled as with lowercase letters in this example. So Euler demonstrated that you could not stroll, and you could check it out yourself. You can't start in one land area and stroll without repeating a bridge. You could get to, if you started at C, you could get back to C if you crossed a bridge several times, or if you didn't cross any bridges, any certain bridge. But it wasn't possible to cross exactly once across each bridge and return to the starting land area. Now, you might say, what in the world? Who cares? Well, mathematicians cared, and it was the start of graph theory. So if you turn this diagram into the graph that it represents, you could see that you could do some algorithms and understand that you can't get back to vertex C, for example, without crossing. In this case, I didn't cross D or F, but I got back to C. So on the 306th birthday of Leonhard Euler, Google published this little diagram, and down in the lower corner is a description of the graph, the start of graph theory, for what that's worth. So there's a bunch of problems. There are a bunch of problems that involve graphs, and which can be solved or shown to be very difficult using graphs. Can any town be reached from any other town? The connected, undirected graph problem. Can we still reach every town if some roads are changed to one-way streets? So that was my problem in downtown DC when I went on my consulting gig and couldn't find my way back home because every other road I came to was cut off and was down for construction, and when I wanted to cross over, it was a one-way street. But that's the strongly connected digraph problem. The spanning tree problem: which roads can you close for repair so that you'll be able to reach everything in town? That's the spanning tree problem. The minimum spanning tree. We want to minimize the number of roads that we would shut down, or minimize the distance that you would have to travel. Shortest path problem. What's the route that minimizes the edge weights between two vertices? The Hamiltonian path problem, the bridges of Königsberg problem that we talked about a minute ago, and one of the hardest ones, the traveling salesman problem. Now, the traveling salesman problem, just for your info, is what's called NP complete, non-polynomial time complete, which means that it's basically exponential. The word exponential is misused in a lot of general talk, but this one really is exponentially hard and one of the hardest graph theory problems. So here's a little bit about how we depict graphs, just like trees, in terms of the vertices. The edges are either directed or undirected. One thing is the bottom line here. You never mix lines and arrows in a graph. So it's either directed or undirected. So here's a set of vertices and edges. A graph is a set of vertices and edges. These are undirected, digraphed and directed and weighted graphs. Now we computer programmers are lazy people, so we don't want to say directed graph every time. We say digraph and leave off the last two syllables of directed. And adjacent vertices, if it's an undirected graph, then A and B are adjacent because you can go either way, and A and C are adjacent, but B and C are not adjacent. So here's some undirected complete graphs. They're complete because they're not disjoint. There's no nodes, no vertices that are hanging off by themselves. Various other directed graphs. These have a directed graph. A digraph has arrows, so you can only go from, in this example, you can go from 0 to 1, but not back from 1 to 0. And here's various weighted graphs. So we have the same terminology. A path is a sequence of edges from one vertex to another. So from B to H, one path is DHI, the edge is DHI. A cycle has the same first and last vertex. A simple cycle is ACK, the edges. And the path length, if it's not a weighted graph, it's just the number of edges in the path. If it's a weighted graph, then the path length sums up the sum of A plus C plus K. But in this case, it's just 3 because it's not weighted. So two vertices are connected if there's at least one path between them. And a fully connected graph is connected if any two vertices are connected. So this graph to the lower right is not connected because once you start from C and go to A, you can't get back to C. A complete graph is a graph where all the vertices are connected to every other vertex directly. Now you may wonder why it's so hard to get a word in edgeways at Thanksgiving dinner. Well, that's because you've gathered the whole family around the same dinner table and there's a complete graph. In other words, if you're person A and you're trying to talk to person D, you can do it. But person C might be talking to you at the same time and person B might be talking to person D. And so that a complete graph is the idea that there is a channel, there is an edge between every two vertices. So how do we represent graphs? Well, there are three schemes that we use. There are two schemes that we use if we know how many vertices there are, and there's one scheme that we use generally if we don't know how many vertices there are. So if we know how many vertices there are, we can represent them as an edge list, as an array. If we represent it as an array, then each vertex can have a linked list of vertex numbers that they connect to. So V0, in this case, node 0 connects with 3 and with 4 and with 1, 1 and 3 and 4. And vertex 1 connects with 2 and 0 and 3, 0, 2, and 3, so forth. By the way, this graph right here, you'll become very familiar with it. We're going to use it a lot in the upcoming slides. So here's an adjacency list of this graph. We know how many vertices there are, so we can represent it. It asks you to draw the adjacency list, and there's the adjacency list for that. There's also, and this becomes more and more useful, there's our familiar graph, and this is what's called an adjacency matrix. The adjacency matrix is a very ubiquitous data structure, and basically it says for node 0, you can go, if you go down the rows, node 0 can connect to node 1. So there's a 1 there. Node 0 cannot connect directly to 2, so there's a 0. Node 0 doesn't, we say that there are no circular cycles. There could be in some graphs, but we don't have any in ours, in our view. So there's no edge to go directly from 0 back to 0, but you can go to 3 and to 4. So that's what and then because it's a digraph, an undirected graph, the array, the adjacency matrix, is symmetrical along the major axis. You'll notice so you can go from 4 back to 3, or you can go from 3 to 4. Now, oftentimes we have this data structure here, which points to, in the heap, the actual object that we're referring to. So here's an adjacency matrix of that graph, and we're asked to draw another one. There's the adjacency matrix of the other graph, of the second graph. Now here's our favorite graph again, and you might have two singly linked lists. If you don't know exactly how long at the start of this representation, you don't know how big, how many vertices there are, you could have a linked list. So here's a summary of the 3 representations. If you know how many vertices, you could use the left or the 2 left ones. If you don't know, you'd use the right one, a linked list of vertices instead of an array. The one we tend to use is the one with the adjacency matrix at the top. Okay, so we have our 4 basic operations in key field or node number. Now I mentioned before that if you delete a vertex, you have to delete all the edges that are adjacent to it, because an edge doesn't live out by itself without an endpoint. So here's the insertion algorithm, the initialization algorithm, the insertion algorithm. One by one, you got to add them to the matrix, to the adjacency matrix. Here's how you would output an edge emanating from vertex V. Now, there are two general ways to traverse a graph. And in general, for a binary tree, you have depth first traversal, which are the six letters, LNR, N, L, R, and so forth. The six combinations of L and N and R. Those all represent depth first traversals. So a depth first traversal visits, now the thing to remember is a depth first traversal visits all children before it visits any siblings. The opposite is true of breadth first traversal. It visits all the siblings before it visits any descendants. So you can use a queue for breadth first and a stack for depth first. Here is so depth first visits all the, and don't worry about the spelling because this is not an English class. All of a vertex descendants are visited before any of its siblings are visited. So you can use a stack, as this slide explains, but you'd have to. So let's walk through it. Let's say you start with vertex 0. So you push V0 on the list, and then you push V1, and you just do them in order. And you push them according to what's adjacent. If you start at 0, at vertex 0, you push 0, and then you push 1, and then you push 4. Those are the only ones that are adjacent, directly adjacent to 0. Because you visit all the descendants first. So you would visit 3 if you push V4. So you push V4, I'm sorry, you push V3 last. And so you pop V3 and you visit it. And then you pop V4. Now there's nothing more to push from vertex 4, so you pop the next element and visit it, visit V1. But at V1 you also have V2 that you can visit, so you push that and then pop it, and then you pop V0. So that is the depth, represents a depth first traversal. Use a stack. So here's some code to show how that works, and I'm not going to go through the code. Here's a depth first search, and the question is there a path from Austin, where it's Austin? Austin is over here, to Washington. And so we see right away that there is a path, but we'll use the computer to figure that out. So using the stack, we push and then we pop Austin. And then if Austin is the end, no, so we write it. And we push all adjacent vertices on the stack. So Dallas and Houston get pushed on the stack. And is the stack empty? No. And have we found Washington? No. So we keep going. And we pop. And we check. Is Houston equal to Washington? Not even close. So we write it. And we push all adjacent to Houston. Things that have not already been pushed. Well, there's only one adjacent element because you can't go backwards through an arrow. So Houston only has one. So you push Atlanta, and then you pop and do the same thing. So now we push the next node, the next adjacent node. Now we don't from Atlanta, we might think that you would push Houston back on the stack, but you don't, because it's already been on there. It's already on this list that's written out. So we don't push it a second time. So now we pop Washington, and we write it, and we set found to true because we found it. And so now we exit. So breadth first happens the same way, similar way, except we use a queue instead of a stack. So we traverse things in the same order because in breadth first traversal, no, not in the same order. This is the order we traverse things in. So here's this queue, and the queue enqueues V0 first, then it enqueues V1, and then it enqueues V4. The difference is that these things are switched upside down. But we dequeue, or pop, if you want to use the stack terminology, and there's the nodes that we get. So that is a breadth first traversal. Now this slide doesn't go all the way through. But notice it needs a front and a back pointer because of the way you've constructed a queue. Okay, so that's the basics of graphs. And I want to end here and pick it up with the next slide in a few minutes about graph connectivity.